Good day, students, and welcome to 7.2 Estimating a Population Mean. All right, in this one, we're going to do the same thing that we did in 7.1. We're just going to work with a couple of problems, and of course, I always like to do stuff with chocolate. So we'll do the Hershey Kisses problem, and maybe if we have a little more time, then we'll do airport data speeds. And that should give us a couple of good examples that we can use from now on. Okay, both of these are in your textbook, page 341, problems in the textbook for section 7.2. And we'll go from there. Okay, ready, set, here we go. Now, I would recommend that you read all of section 7.2 before you watch this video. You just want to have a really good feel for what we're doing. And just so you know, our objective really in this chapter, the objective that we have is we want to construct a confidence interval. Construct a confidence interval for means. Okay? And means in this case have to do with a sampling distribution and all of that. But if we're going to do that, then we're going to need some notation and some things that we need to find and be able to use. We're going to estimate the population mean. We're going to use the sample mean in order to do that. We're going to also use the sample standard deviation to help us do that. We'll need the number in the sample, and we're going to work to find, this is going to be what we're going to find, which is the margin of error. There will be some requirements for this. Essentially, when you deal with data, you have what are called small and large samples. A small sample tends to be less than 30, and a large sample tends to be greater than or equal to 30. Now, if we have a large sample greater than or equal to 30, then the sampling distribution of in there is always going to approach a normal curve. And so if we have a large sample, the method that I'm demonstrating today is going to work. In general, though, we're dealing with small samples. Most time, that's what we're dealing with, where the sample sizes are less than 30. And that's going to cause us to have to use a new distribution called the student's t distribution. This is a nearly normal distribution. It varies a little, and it's what we have to do to compensate for the small sample sizes and the sampling distribution not approaching normal very fast, especially if these are not as close to normal as they should be. Some other things that we're going to pay attention to are called, we're going to find the margin of error. We're going to talk about what's called confidence level. We're going to also talk about critical values, which we did in the last video as well. And we're going to need to deal with something called degrees of freedom. So those are some vocabulary, and we'll touch on those things. Degrees of freedom tells us which student t distribution to use. Confidence level and critical values and margin of error we'll talk about here in just a moment. Okay, so those are the main things that we are looking at. By way of introduction. So as you're reading the chapter, you want to go through and kind of go through each of those things and make sure you're clear on what their meanings are. All right? And then I'll try and explain them as we go through the problem as well. So what we have done, here's our data, and this is pulled directly from the problem over here. And what we have done is we have taken a sample of size 32 Hershey Kisses in a bag, and we have weighed those Hershey Kisses and come up with a sample weight of 4.5210 grams, okay, for the mean. All right, a sample mean of 4.521 grams. And we've come up with a sample standard deviation of 0.1077 grams. What we want to do is we want to find a confidence level of 99%, or we want to find a confidence interval with a confidence level of 99%. Now, the problem asks us right here, we want to do 4 things. We want to find the critical value t sub alpha over 2. What is that? Okay. We want to then be able to find the margin of error. Okay. Just so you know, the margin of error is just a formula. And so once we know t sub alpha over 2, we plug in the formula. It works out pretty easy. Then we want to find the confidence interval. So we want to actually find the confidence interval. Okay. And we then, we want to interpret our confidence interval. And so let's talk about confidence intervals before we actually do it here. What do we actually do with a confidence interval? Okay. So what happens is I take this sample of size 32, all right, and let's say the true mean is here, okay? And so I don't know what that true mean is, but I want to estimate it. So I take a sample, and I have a sample of 4.521. And I don't know where that would actually be here, but we're just going to pretend it's right here, 4.521, okay? And it's an estimate. It's a little smaller than what we would want. It's very close. It's only a few thousandths away. Here's our estimate. Now, when I say I want to make a 99% confidence interval, then what that means is with the 4.521 in the center, I'm going to find the lower number and a higher number, and I therefore will come up with an interval. So this will be the sample mean minus the margin of error. So this distance here is the margin of error. And what we do is we subtract that margin of error from the sample mean, and we add it to the sample mean. And that gives us an interval. And if you guys remember intervals, it's basically another way to write an inequality. So we could call this an inequality estimate if we wanted. But that will give us an interval. This interval, I'm going to be 99% confident that the true mean is in that interval. All right? And, well, I'm not confident that the true mean is there. I'm confident that the interval contains the true mean. So I'm confident in my process of building the interval. Now, basically what that means is if I take essentially 100 samples of size 32, and I take all their sample means, their sample means are not going to all be the same thing. They're going to end up scattering around this sample mean, and therefore their intervals are all going to be different. And basically what's going to happen is about 99 out of 100 of those intervals are going to contain the population mean. I don't know what it is, but they're going to contain it. One of them will not. All right? And that's what the confidence level means. And that's sort of our process for getting there. So that's why I want to find the error. But in order to find the error, I have to find T sub alpha over 2. So what is T sub alpha over 2? We need to talk about that. Okay? Just like when we talked about Z sub alpha over 2 on the proportion intervals, T sub alpha over 2 is essentially a similar thing. What happens is we have a curve. In this case, it's a T curve, which looks like a normal curve. They're also bell-shaped. That looks like this. All right? And that curve is centered on our sample mean. Okay? Pardon me, I said that wrong. That curve is centered on 0. Just like the Z values are centered on 0 for the normal curve. Now, somewhere out there in the ether is this data centered on the sample mean, 4.521. So there's this curve and there's this curve. And what I want to do is this 4.521 is going to correspond to 0. Okay? And so I want to find the T value. So if I make a 99% confidence interval, okay, that means everything in between here. So if I color in between these two lines, all right, that's 99% of everything. And then outside this, I have 1%, which gets split into two pieces, 0.005 and 0.005. And so if this is 0, and this is 99% in between, if I go for the areas 0.005, there's a T sub alpha over 2, and what's alpha over 2? It's T sub 0.005. Or if you take the 0.005 from 1, it's T sub 0.995. All right? And between 0.995 and 0.005, that's 90, that's our 99%. Okay? And so that's where the T sub alpha over 2 comes from. And so we want to find that value. The easiest way to find that value is to use a table. But you can also use a calculator. I'm going to try and show you both. Okay? Number one, the table, to look it up on the table, you need to know one thing. You need to know the degrees of freedom. The degrees of freedom come from the sample size. Since our sample size is 32, the degrees of freedom is equal to 32 minus 1, or 33. Oh, excuse me, 31. 32 minus 1 is 31. So our degrees of freedom is 31. So when we go to look at the table, we're going to look at 31. And so here we are looking at the t-distribution table. This is in the back of your book on page 734. Okay? And when you look at this, you're going to look for 31 degrees of freedom, which is right there in that circle. And you're going to get your critical values by looking across. Excuse me, I apologize. Anyway, which ones do we choose? Well, we need to know what's the area in one tail. And if you look, our area in our tail here was 0.005. It was the area, and then of course the area in this tail was 0.005. So the area in two tails is 0.01. It's whatever's left over from your confidence level when you subtract for 1. And so in that case, we're looking at the first column. I apologize, some cooking's going on in the house, and I live in a tiny house. Oh well, here we go. So that's why I choose the first column, because it gives me the area in either one tail or two tails. Two tails is just the confidence level subtracted from 1, and then one tail is that cut in half. So now we have that, and that's why I said it was t sub 0.005. That's what the t sub alpha over 2 was in part A that we needed to find. Part A was t sub alpha over 2 is equal to t sub 0.005 is equal to, right there, that number, 2.744. 2.744. Okay? And that's how we get the t-value, by using a table. Once I use the table, then I can find the margin of error. And so the margin of error is equal to, and I have that listed over here, sorry, t sub alpha over 2 times the standard deviation divided by the square root of n. So it's t sub alpha over 2 times the sample standard deviation divided by the square root of n. So that's just a formula. What's this give us? Well, this converts, remember I drew two t-distributions, and up here I had the 0.99 area, and this was 0.005, and I said it was centered on 0. Well, this one's centered on 2.510, the sample mean, or excuse me, it was 4.5. It's centered on the sample's mean, and the margin of error gets converted to that. So we take this t-value and we multiply it by the standard deviation over n, and that gives us how far we have to go out to this value, whatever that value is, and this value here, by adding and subtracting the error to this mean, this sample mean, 4.521. Okay? And so we can calculate that 2.744 times the standard deviation, which was, let's look, I forgot, 0.1077. 0.1077 then divided by the square root of 32. And so we can do that on a calculator. And I've now done it on a calculator, and I get 0.0522. That's the margin of error. So now I can do part C, which is calculate the confidence interval. So I can take 4.5210 and subtract 0.0522 and 4.5210 and add 0.0522, since that's the error. And that's the formula, and the formula for this is x bar plus or minus the error. And so that's what I'm doing there. So I do that on a calculator. And once I do that on a calculator, I get two numbers. I get a smaller number and a larger number. The smaller number is the left boundary on a number line for the confidence interval, and the larger number is the right boundary. Remember, when we look at this graph with 4.521 in the middle, this is a number line here. And so the 4.57 is right there. And this one here is the 4.46. And in between those two numbers, that's our 99% confidence interval. And so we're estimating that the true mean, which may be equal to the sample or not, unlikely that it is, but we're estimating that the true mean is in this interval somewhere. And we're 99% confident that that interval contains the true mean weight of Hershey Kisses. And so that's our final part to this problem, our conclusion. I am 99% confident that the interval contains the true mean weight of Hershey Kisses. And that's how you do these problems. Oh, now that we have the conclusion, we'd probably like to do one more. And if you're concerned about that conclusion, I would suggest you look at what page in your text. Let me see if I can find it. We are 99% confident that the interval, and I would list the interval 4.46 to 4.57 contains the true mean, and you could put grams on that. You would put grams. I'm trying to see, do they talk about that in the text? Gosh, I think it's just in their examples then. When we do hypothesis testing, they make it kind of a big deal, and they actually separate it out. But as you look at the examples in the reading, they will write the conclusions as I have written them. Okay? All right. Let's get on to another problem. So number one, we check the conditions and see if if those are met. So we can assume that number 8 is a simple random sample. A simple random sample, that's a condition. We can assume that the population is normally distributed or the sample size is bigger than 30. And what we see is our sample size is 38, so it is bigger than 30, so we're good. So therefore, let me see, sample size greater than 30. That means we can use the student's t-distribution to evaluate this, okay? And so we want to make a 95% confidence interval. 95% confidence interval, okay? That means that we have a normal curve with 95% of the data in between here. This normal curve is centered, okay, on the sample mean 18.86. All right. Our goal then is to essentially find this value here, right here. I'm trying to think, what's it labeled? Oh my gosh. Oh, this will be x bar minus the error, and this one will be x bar plus the error. Now, what we need to do in order to do that is we have to go to the standard normal curve, which is centered on 0, and, excuse me, not the standard normal curve, a t-distribution, all right, centered on 0, and we want to find these two values, which are called the critical values, which is t sub alpha over 2, all right? So, since we're finding a 95% confidence interval, 95% is equal to 1 minus alpha, and therefore 0.005 is equal to alpha, so 0.05 is equal to alpha, so 0.025 is equal to alpha over 2. So t sub alpha over 2 can actually be written as t sub 0.025. What's that mean? All that means is the area here is 0.025, the area here is 0.025, and the area in between those is 0.95. Okay? So that's sort of the standard normal curve. We can get this value from the proper point on the t-interval table. To do that, we need the degrees of freedom, which is equal to 38 minus 1. The sample size minus 1, that's 37. So we're going to look at the table at row 37, and we're going to look at the area in one table being 0.025. So where those two rows intersect is right there at 2.026. Okay? So this t value is 2.026, negative since it's below 0, and it's a positive 2.026. All right? The next step in the problem then is to write the interval. Well, what's the interval? The interval is x bar minus the error, comma, x bar plus the error. That's the interval. And so x bar was 18.86 minus, and the error formula is, I'll write it again here, is t sub alpha over 2 times the standard deviation over the square root of the sample size. Okay? And therefore, that's minus 2.026 times the standard deviation 15.66 divided by the square root of 38, the sample size, comma 18.86 plus 2.026 times 15.66 over the square root of 38. Okay, I'm going to figure both of those out using the calculator. And so our confidence interval is 24.007 to, oops, got that on the wrong side. 24.007 is the bigger number, and the smaller number is 13.713. And so this is our confidence interval. So what's our conclusion? Our conclusion is we are 95% confident that the interval 13.713 to 24.007 contains the true mean, and the problem is true mean phone data speed of phone data speed in airports. Okay, period. And you can label these in the interval with the label, and I think it was megabits per second, which was the data speed. And that's the conclusion. Now, how do we understand these conclusions? The conclusions help us to understand what we're looking at in this way. If you remember on the last problem, there's a true mean, but when we do the confidence intervals are around that true mean. And basically in our case, if we had 100 of them that we created in this way from 100 different samples, we would expect 95 of them to actually contain the true mean. And some of them are gonna, just miss it, all right? So that's kind of the idea behind a confidence interval. Okay, we've constructed 2 of them now. That's the basic process. So what else is in this section? There are a couple other things in this section. One of those things is you want to find sample size. So how would you do that? Well, if you knew the confidence interval, you could work backwards to find the error, okay? So for instance, suppose this was our confidence interval, 13.713 and 24.007. And all we knew was that was the confidence interval, okay? And what we wanted to find was the sample size. Well, first of all, if you take 24.007 plus 13.713, that will equal 0 to 7, and then 13 and 24 is 37. And if you divide that by 2, you'll end up with 1, 8, 8, 6, which would be the sample mean. Now notice that matches our original sample mean. So this is a way we could find the sample mean if all we knew was the interval. Again, if all we know is the interval, we could actually find the error as well. So you take, in this case, instead of adding them together, you subtract them, and you can do this on a calculator, of course. And when you subtract them, you would get then the value of the error. Now, I didn't find the error separately like I did before, but if I did, this would be the value of that error, 10.294. And then we would add and subtract that to the sample mean, which is what we did. We just did it as one problem last time. But now you can find the error separately just by knowing the interval. So that's another problem. If you know the error and you know the sample size, if you know error and sample size, or not sample size, standard deviation, then you can find the sample size by, again, working the problem backwards, okay? And so we have the mean plus the error, right? Which is the mean plus t sub alpha over 2 times s over the square root of n, all right? And so, I don't need all that. I just need that the error is equal to t sub alpha over 2. If you know this, then, formula, then you could solve for any one of these variables if you know some of the other variables. That's kind of the key, all right? And so that gives you a way to figure out what the sample size was. Now, your textbook has some examples of these things. They're kind of some extra bonus stuff. You want to make sure you read through those and you understand how they work. Okay. Let me see. What else do I need? Overall, I think that's it. Okay. Now, there's more to this, and if we had a class, if you want some more information, you can always ask and in an email, and then I can send you some more. But a good careful reading and then slowly going through each of the problems will help you be able to do this work. So I'll see you later. Good luck. Bye.